And this is a normal distribution question from 2011 AJC. Okay, paper 2 of course, and question 9. Alright, so let's quickly take a look at this particular question and see what is the challenge here. So there is LCD screen, let's simply call it A. A is normally distributed, so maybe I should just write it here. So A is normally distributed with a mean of 45,000 big numbers. Okay, and standard deviation is 2,000, so remember to square it. Okay, so this is the distribution of A, whatever it is. Alright, plasma TV B is also normally distributed, so B is also normally distributed. So the mean is, oh, interesting, they don't tell us the mean, but they tell us the standard deviation. So the standard deviation is 1,850. Okay, and what's the mean? So it tells us here that, okay, there is a 50% chance that the lifespan of B, basically B, less than 30,000. It's 50% chance. What this really tells us is that knowing that B is a normal distribution, sorry, wrong color. Okay, knowing that B is a normal distribution, therefore the bell curve will apply. So 50% chance obviously refer to the symmetry, and therefore what they're trying to tell us is that the mean is actually 30,000. Okay, so 50% chance is less than, so which is here. So this is the 50% chance. Okay, so well, the mean will then be 30,000. Okay, looks like we have the information for A and B. So let's take a look at part 1. The LCD screen, which is A, and 2 plasma TVs are randomly selected. Okay, show that the probability that twice the lifespan of the LCD exceed the total lifespan of 2 plasma by this is this. Okay, sounds a little bit complicated as well as quite a mouthful, but really what it means is that there is one A and there are 2 Bs going on. Okay, so twice the lifespan of A. Let's take a look. Let's do it over here, part 1. Okay, so based on the information we know, what we want to be able to do is, of course, we are talking about 2A. Okay, twice the lifespan of the LCD, which is A. So twice refers to multiply by 2. So we will get 2 multiplied by 45,000. Okay, and of course for the what you call that, the variance, we will take 2 square, okay, multiplied by 2,000 square. Okay, so our 2A will follow a normal distribution of from our trusty calculator we have 90,000. Okay, and of course the variance, of course we need to simplify this, so the variance looks like, oh my goodness, quite messy. How many zeros is that? 1, 2, okay, so hold on, 1, 2, 3, 4, 5, 6. So alright, 1, 2, 3, 4, 5, 6. So 16 million. So that will be our variance. Okay, kind of scary number, but yeah, this is our 2A. Okay, what's going on next? There will be, of course, there will be 2 plasma. That means again 2B, 2 independent observations of B. So what are we talking about is actually B1 plus B2. So bear in mind the difference between adding and multiplying. So B1 plus B2 is not really quite the same as 2B. Okay, so we follow normal distribution, and we'll multiply by 2 to the 30,000. Okay, and of course we multiply by 2 to the 1,850 square. So this will be our new what do you call that, variance. Okay, so B1 plus B2 will follow a normal distribution, of course, 60,000, and again a big number over here, which is 6845000, and that is 6 million over. So there you go. Alright, what is actually important for us to help us do part 1 is we need to know the distribution of 2A as well as the distribution for B1 plus B2. So what is going on here is this. What they want is the probability. Okay, let me highlight to show you what's going on. So probability that twice the lifespan of the LCD exceed the total lifespan of 2 plasma by at least Okay, what this means is really we are trying to find the probability that the 2a is being more than the b1 plus b2, in other words minus the b1 plus b2. Okay, and this difference has to be by at least means inclusive, right? So by more than 25,000 hours. Okay, so this is what the question is trying to ask us to do, and of course before we even do that, we need to take this distribution 2a and minus away this distribution first. Okay, so well, we're running out of space, so we need to scroll up a little. Okay, so before we can even find this, we need to like I said, okay, need to work out this distribution proper. So you will still follow a normal distribution, and of course the mean will be this 90,000 minus away this 60,000, and okay, not that difficult, right? So it's 30,000. Okay, and the variance, bear in mind the variance we never minus, okay, subtract, so we always add. So adding these two humongous number together, we get something close to 22,845,000. How nice if you have this number in your bank account, right? Okay, so anyway, 22 million, just make sure we get the correct number. Okay, good. So this is the distribution for this, and therefore the what is left to do is just using your GC. Okay, because I believe this is pretty easy and straightforward, so I'm not going to waste too much time to show you the screenshot of how does the GC look like. Okay, but I'm quite sure you know what to do, right? So you go to normal CDF. Okay, you key in the lower limit, which will be then your 25,000. 25,000, yes. Okay, and then the mean, which is the 30,000, and of course the standard deviation. Please remember the square root so that you get the standard deviation into your GC rather than the variance. Okay, and of course if all things are alright, we will get the answer of 0.8522, which if we were to round off to 3SF, that would be what they want us to show, which is 0.852. Okay, here you go. So this is part 1. Alright, so let's move on to part 2. A batch of 50 plasma TVs is produced. Find the probability that more than 14 but fewer than 22, alright, have a lifespan of more than 30 hours. So this sounds like a binomial distribution because we are talking about whole number first of all. Second, there's a maximum number of plasma TV that's produced, right? So the maximum number is 50. So alright, let us scroll down a little. Okay, so what we do would be for part 2, we need to redefine our random variable. Since we haven't used x, that'll be a good idea. So let x be the number of plasma TV. Okay, plasma TV. Right, which is having a lifespan of more than 38,000 hours. So this is the probability of success. So this is a success. Alright, out of 50 TVs. Okay, so the important points, I think I mentioned many times, of course, is the number of something, and this is the success. Success being the lifespan having more than 30,000, and of course the n, which is the total number of trials, which is your 50. So we need to define our binomial distribution proper. So x follows a binomial distribution, 50, comma, the probability of success. In this case, we need to figure out what's the probability that a plasma TV having a lifespan of more than 30,000. So we need to go back all the way to this, and we figure out that hey, it's actually not that difficult because more than 30,000 is basically here, so it's 50%, right? So it's 0.5. So the probability of success is actually 0.5. Okay, so that's easy enough. Let's move on to to see what they really want. So what they want is more than 14 but fewer than 22. What it really means is hold on, let me more than 14 fewer than 22. So what it really means is that what they want is x to be more than 14 but fewer than 22. Alright, so there you go, this is it. But this kind of calculation will be a little bit more troublesome to calculate using our GC because of the way that our GC is is, right? So we have to use a little bit more. I mean, we're going to have 2 steps involved. So anything that's less than 22 is actually 21. Okay, less than 21 or an inclusive 21. So we minus away what we don't want is actually up to and including 14. Alright, so do take note of this. Alright, and this is something that many students tend to get careless at this point, which is totally wasted. So let's just try to understand what we want. Okay, so according to the question, what we want is really x equal to 15, 16, 17, 18, 19, 21. So these are the numbers that we want, and therefore what we're doing here is we're adding from 0, 1, 2, 3, 4, 5 all the way until 21, minus away from 0, 1, 2, 3, 4, 5, 6 all the way to 14. So get the point? Yep. So we end up with 15, 16, 17, 20. Okay, so this is something pretty basic, which I suppose most of you should have no problem. Alright, so using our GC, we should be able to calculate out this pretty easily. Okay, we should be able to get the number of 0.16122 minus away 0.00130011. Okay, something close to that. So of course, if you round off to 3SF, it should look like 0.160. Okay. Alright, so this is it. This is part 2. Relatively easy question for AJC, isn't it? Alright, so we got 5 marks already. So let's take a look at the third one, right? The one I'm supposed to be a bit harder. So find the least value of n such that the probability of the average. Okay, average means mean. So gotta be careful here. Of mean lifespan of n LCD. So we're only talking about LCD, which is the distribution for A. It's at most these so this is the probability and this is the limits that we're talking about. So but the most important thing is that we're talking about mean. Okay, in other words, we are going to have n number of LCD screens, so maybe we need to copy down the A all over again, right? So 45,000, 2,000 square. Okay, so let me just scroll all the way. Alright, so part 3. Okay, so what we know is that the LCD screen has this distribution of 30,000 as well as 2,000 square. Okay, let's just double confirm that I don't screw up. Okay, 45,000. Yeah, I did screw up. Okay, hold on, let me just change this number a little. Okay, so it's 45,000, not 30,000. Got it wrong there. Alright, so 45,000. Okay, there you go. So now what we are going to have is, now imagine that we have so many TVs. So there are total n of them. Okay, and I'm going to add them all up and divide by n, and therefore it becomes A bar. Alright, which is the mean, the average of the lifespan of the A, right? So according to what we learn, the distribution for A bar will then become 2,000 square over n. Okay, now if you're not too sure what am I doing here, just imagine that. Okay, let me maybe just quickly run through review, because this is a normal distribution, so no CLT is involved here. Alright, imagine that we are going to have A1 plus A2 plus dot plus until AN. So there's so many of them, right? This will follow normal distribution, of which 45,000 n and 2,000 square n. Okay, and A bar simply means all these sums. This sum of all the TVs added up together divided by n, isn't it? So it actually means 1 over n multiplied by all this distribution. This A1 plus until AN kind of thing. In other words, remember that when we do multiplying, we have to multiply by the square. So in this case, dividing by n is actually multiplied by 1 over n. So the A bar is actually following normal distribution, of which we'll take 45,000 n multiplied by 1 over n, which is divided by n, and we will take 1 over n square and multiply by this 2,000 square n. Okay, so of course common sense will tell you that this n and this n will cancel, but this is where it gets interesting, because there's only one n here, but there'll be two n's at the bottom, so which is why it becomes like this. Okay, so it is very this is actually in the same chapter as sample mean. Alright, so something quite interesting. But there's no need for CLT because this is already a normal distribution. Okay, so let us go back to the question because I forgot what they wanted to ask, right? So what they want is find the least value of n such that the probability, so the probability is given to us, okay, at least 0.99, at most 46,500. So what they're trying to say is this: the probability that a bar at most means less than or equal to 46,500. Okay, this probability is at least 0.99. Get the idea? Okay, now we are faced with a special problem here, which is not so uncommon in the sense that we are dealing with a normal distribution that we don't know the parameter, which is in this case our standard deviation or variance. Right? We don't know what is this value. In other words, check this out. We are looking for n. We are not looking for the limits. We are not looking for the probability either. So in this case, we have to do the standardization in order to help us solve this question. Okay, so standardizing, this becomes z, and of course this becomes 46,000. Sorry, 450 whatever. Okay, minus away 4. Hold on, this is 465,000. Am I right or no? Oh, I'm so sorry. It's 46,000. One more zero. There you go. 46,000, not 450,000. Okay, let me erase this one zero away. Yeah, otherwise, of course, we get the wrong answer, right? So, 46,500 minus away 45,000 divided by the square root of this 2,000 square over n. Okay, yeah, this is how we standardize, and it's 0.99. Get the idea? So, of course, from here, we then do the inverse norm to figure out what is this limit. So minus this figure will give us, okay, so what we will know then of course is z less than or equal to 1,500 over 2,000 over square root n. Okay, and will be more than or equal to 0.99. So of course we can simplify a little bit further. Okay, so let us go and do that. So 1,500 square root n over 2,000. In fact, you can even cancel away if you like. Okay, so, but actually it doesn't matter. So we get this. Okay, so going to our GC, because it's already in the left bound area, right? So going to our GC, we will get this is what we're going to key in, right? We're going to key in inverse norm. Okay, of course 0.99 being the area, the mean will be 0, variance will be 1 because it's a standard normal distribution, right? So we will get the answer of let me see, 2.326. okay, I think this is good enough. So therefore what we know, okay, so many dots here, 15, okay, this can be cancelled away with this. So 15 over 20 actually can simplify some more, but not necessary. So it will be more than or equal to 2.326. So after we simplify further, we get 3.101. okay, and squaring both sides, we will get 9.62. in other words, n has to be greater than 9, n has to be 10. Okay, so there you go. This is it. This is for part 3. So let's quickly take a look at the last part over here. Explain which of the probability is actually greater. This is a very weird question, but it's only 1 mark. So obviously, I don't think you will need to go and do the calculation and try to convince people that definitely this is greater than this, or this. It's only 1 mark. So I'm quite sure it's an explain type of question. In other words, means if you're convincing enough, you get the marks. Okay, if not, if you try to convince, if you cannot convince, you try to confuse, right? So since it's a very short and sweet question, I just maybe change my color and just do it here. You need to then understand that if you have a plus b, generally if you think in terms of sets, okay, well, a plus b is basically here, right? The whole thing, a plus b, okay. So if a is more than 25,000 and b is also more than 25,000, when they add both together, obviously a plus b must be more than 50,000. Okay, in other words, this part 1 is actually a subset of this part 2. Okay, because hold on, no, I think I'm said something wrong. Okay, the part 2 is actually the subset of part 1. Yeah, this is more correct, because part 1 actually encompasses part 2. Okay, in other words, if this were to be true, okay, then this will have to be true. Okay, this is a smaller set than this, and this is a subset, and therefore we understand that part 1 will be the greater probability. Okay, and simply because part 2 is a subset of part 1. Right, so for 1 mark, I think this is good enough.